So now let's get into thermodynamics of ionic solutes in water. And so with thermodynamics of ionic solutes, basically we're talking about, the enthalpy of solution. And our enthalpy of solution can be positive, or, something that's endothermic and takes heat for the solution to be created. Or we could have our enthalpy of solution to be negative, and then this would be something that would give off heat or be exothermic. Right, this is really kind of talking about the breakdown of the forces of attraction that we alluded to earlier, that, the enthalpy of solution is dependent on a couple of things. One would be the enthalpy of the solute plus the enthalpy of the solvent plus then the enthalpy of the mix or the mixture. And so what we have to recognize is that these are just looking at energies for breaking down forces or creating new forces of attraction. So this is where we're, the energy to, break down solute forces. While here with our delta H of solvent, it's very much the same. This is the energy to break down solvent. Forces of attraction. So again, that's that idea that each one of these has to make room for the other, that the solute has to make room for the solvent, and the solvent has to make room for the solute. So that means that there's this breakdown of forces of attraction to create that room. And then we have, energy released upon making new solvent forces. So depending on the energetics, we can get things that are plus and things that are negative. Since we are specific with H2O as our solvent, and ion dipoles as our new force in the mixture, we find that there's a combination known as hydration. And this equals our enthalpy of the solvent plus our enthalpy of the mix. So since we're specific, we can actually take this equation at the very top and make it a little bit more simple, where we have our enthalpy of solution is equal to the enthalpy of the solute plus now the delta H of hydration, which is what we're seeing here with that combination of those two terms. So that's again because of just the specifics that we're seeing with water. We are specific with H2O And we're also specific with our ion dipole as our new force because we're talking about electrostatic forces of attraction or ionic molecules being dissolved. So that brings up another point, and since we are also specific with ionic solutes, the delta H of the solute can be, put in terms of lattice energy. So we could say that the enthalpy of our solute is equal to the negative of our enthalpy of our lattice. So realize that the lattice energy is that energy released upon two ions coming together to form an ionic solid. But with the solute idea, we're looking at breaking down forces of attraction, trying to break those down into different ions. And so that's why we see the opposite sign, where this is the energy required to break into separate ions. But on the other side, this is the energy released upon ions coming together. So they're the same idea. It's just which direction are we going? Are we breaking those atoms into ions? Getting rid of the covalent bond. Getting rid of the ionic bonds, or are we actually forming the ionic bonds? And then we have the release. So we find that then there's yet another version of that enthalpy process where we could say, well, the delta H of the solute is really the negative of the lattice energy. And then that would be plus the delta H of hydration. And this is the common one that we see. So let's look at an example of this. Let's look at potassium fluoride. And so we want to calculate the enthalpy of solution for potassium fluoride. So we have potassium fluoride that's aqueous. If the enthalpy of hydration is negative 819 kilojoules per mole, and the lattice energy for Kf is negative 821 kilojoules per mole. So if we look at what we're given here, we're given the enthalpy of solution, the enthalpy of hydration, as well as the lattice energy. So obviously we're looking at the equation that we see above. And so just to break that down, right, we have our hydration given to us as negative 819 kilojoules per mole, and we have our enthalpy of lattice to be negative 821 kilojoules per mole. And so those are both pointing to, our expression to solve for the enthalpy of the solution, which would be the negative of our lattice, right, then plus our enthalpy of hydration. So we have both of those entities. We just have to put them into the right spot. And so the most common mistake we see here is forgetting to change the actual sign of the lattice. So if we plug in our values, we're trying to solve for the delta H of solution. Our lattice energy was a negative 821 kilojoules per mole. Our hydration was negative 819 kilojoules per mole. We have that sign change for the lattice energy. And so our delta H of solution would be a positive 2 kilojoules per mole for the solution of potassium fluoride. And this would be an endothermic solution as a result. So that's looking at the thermodynamics of ionic solids dissolving into H2O. So now let's get into some example calculations of molarity and molality. We already introduced the units, but we haven't done an example in calculating them. So here we go. So we want to calculate the molarity of a hydrochloric acid solution prepared by diluting 150 milliliters of concentrated HCl. Concentrated HCl has a density equal to 1.18 grams per milliliter, has a percent by mass equal to 37%, and the molar mass of HCl is 36.5 grams per mole. So we're going to calculate the molarity of a HCl solution prepared by diluting 150 milliliters of concentrated HCl to a total volume of 5 liters of our aqueous solution. So that's our example problem. If we kind of look at what we have here, we have really have two solutions. We have one HCl solution, which is dilute, and then we have another solution which is concentrated. So even though they're both solutions, they're both HCl and they're aqueous, one is dilute and one is concentrated. And so if we kind of look at all the values that are within the question, here is, something to start with, right? We have here a measurement. It's always good to start with a measurement. And then if we look at all of these values that we have below in terms of our density, our mass percent, and our HCl, molar mass, these are all conversions because we have a numerator and a denominator. So if we, kind of look at where we want to go, what are we trying to do here is we want to calculate the molarity of this dilute HCl. So we could write that, maybe like this, saying we want to know what that molarity of the dilute HCl would be. And so what would that entail? Well, we'd have to know moles of HCl, and we have to also know volume liters of solution. And we actually already have that, end volume of solution being 5 liters. So if we break this down a little bit more, really what we got to figure out is our moles of hydrochloric acid, because we already know our solution volume is 5 liters. So we got to figure out moles of HCl, and somehow we have to use these other measurements to actually, do that process. So we could kind of think about it as a thought process, meaning that I want to figure out moles of my HCl, and how can I actually do that? The most common way to think about getting into moles could be from a reaction, which we don't have here. We're just talking about a dilution. So, another possibility here would be looking at, well, I do know my molar mass is 36.5 grams per mole. So if I could get into grams of my HCl, that will be a way to then get into moles of HCl. So the question is how do we get into grams of that pure hydrochloric acid? And so here's where we might get a little bit stuck. We just have a thought process now that, okay, I want to get to moles, and I can, hopefully get to grams, but how do I get there? Let's now go to the other side of the story and start with that measurement. All right, we have 150 milliliters of the concentrated HCl. It's always, again, a good place, always start with a measurement. When doing conversions, it just makes life a little bit easier because you're going from one unit to the next as opposed to changing, multiple units. So if we go back up to the information, what could we use with that volume, that 150 milliliters of solution? What could we use? And what I see right away is the density, right? We have a density of that solution. So that might be one way to go, right? That we can get at grams of HCl. But we got to be very careful with our language here, right? This is grams of concentrated HCl. And so we can use that density of 1.18 grams per milliliter to get into grams of concentrated HCl. And, okay, now there is my connection, right? I can get in between grams of concentrated HCl to grams of pure HCl by using my 37%, right? My 37% by mass. So I use my volume measurement, my first step here. is to get that into grams of concentrated HCl. My second step is to get into grams of what we would say is pure HCl. And then the third step is getting into moles of the HCl. So there's our game plan, and then that allows us to figure out X moles, and then we can solve for our molarity. So let's start the conversion process. So we have the 150 milliliters of the concentrated HCl solution. And in step 1, we want to convert it using our grams per liter. So there will be 1.18 grams of this concentrated HCl solution for every 1 milliliter of the concentrated HCl solution. So we can get out of our volume and get into our mass, but we're in mass of the actual concentrated solution. So there's our first step. We can then set up the mass percent by saying, well, for every 100 grams of concentrated HCl solution I have, right, there are 37 grams of pure HCl. So there is our second step, now getting out of mass of the concentrated solution and getting into mass of the pure HCl. And then my last step would be taking that mass value and dividing it now by 36.5 grams per mole in terms of my pure hydrochloric acid. And so that is our third step now to get out of mass and get into moles. And when we do that, we should get a value of roughly 1.79 moles of pure HCl. So there is our X value. And so now we can solve for the molarity of the HCl that is now dilute. We have the mole value for the HCl. We have the volume of the solution after we did the dilution. So our molarity of the dilute HCl is 0.358 molar. So trying to get the gears rolling again with dimensional analysis, right, as far as how we can go from one unit to another, but also not just units, but making sure that we're detailed with concentrated, dilute, or pure in terms of things that the units are describing in terms of that. So the second example here would be to calculate the molality of the solution above. The density of water is 1 gram per milliliter as a helpful hint here. So we want to calculate now the molality. We're using all the same values that we had above. So that's what we're trying to figure out. So our molality would be little m, and so that would be moles of our HCl per kilogram of the solvent, which is H2O. And we figured out from above that we have 1.79 moles of the HCl. And so what we don't know in this particular case is the denominator, is that we don't know what the mass of the H2O actually is. So some simple things that we could look at is, we started with 150 milliliters of the concentrated HCl and diluted up to our 5 liters with water. So, a simple difference allows us to determine how much water is added. So that's where we want to begin, though we're going to find that we have to be a little bit careful. So if we take, our total, right, we would say that, 0.150 liters, right, that was our concentrated solution, plus X liters is going to be equal to 5 liters, right? So we have our dilute HCl, we have our concentrated HCl, and then here is the dilution volume. So we could easily, just subtract off our volume. So we would have 5 liters minus 0.150 liters, and so we get a value of 4.85 liters of H2O has been added during the dilution. So there's our volume of the water that we added during the dilution, and we can then convert that to our mass of our H2O by basically using the density. So we have our density of the H2O as 1 gram per milliliter, but we could also kind of change the units in terms of kilograms per liter. Notice I've changed both the units in the numerator and the denominator by 1,000. So the value of the density doesn't change, and that allows me now to take that 4.58 liters and realize that that's actually the same value in terms of kilograms. So I would have 4.85 kilograms of our water has been added. So here's where students will make a common mistake, is they will now just immediately plug this into the expression that we had above, namely just plug it right into our molality expression. But we have to be careful because there's more going on here than simply the actual dilution. We have to be careful because remember that there is, also H2O in the original concentrated solution. So we have to figure that out as well, that we have the mass of the water that we added to dilute, but the original solution was just that. It's an actual solution. So we have to figure out, from the original concentrated solution, the H2O that's actually within that. So that's a conversion similar to what we did earlier, meaning that we can start with that measurement of 150 milliliters of our concentrated HCl and still use that density to get in terms of mass. So the first step, is pretty much the same as the molality part to this example. And here we actually now use the percentage, realizing that if we kind of look above, remember we were at 37% HCl by mass. That must mean we are 63% H2O by mass in terms of that original concentrated HCl solution, right? Always two components, a solute and a solvent. The solute is our HCl, the solvent is our H2O, but both of those components should add up to 100%. So now we can just use the other percent, which would be for every 100 grams of this concentrated HCl, we would have 63 grams of our H2O. And once those cancel out, we get out of our mass of concentrated HCl, get into our pure water, and so we end up with 112 grams of H2O, or 0.112 kilograms H2O, in the original concentrated solution. So we have, two values now, right? One for the dilution, which is the 4.85, and now the original mass of water within the concentrated solution. So our total H2O mass is now, the sum of both of those. So we would take our 4.85 kilograms plus our 0.112 kilograms from the concentrated, and we end up with a value of 4.962 kilograms of H2O total. So we got this 4.85 from the dilution. The 0.112 was in the original concentrated solution, and so now we have our total of 4.962 kilograms. And so now we can solve for the molarity of the process. Remember, we had our 1.79 moles of HCl over X kilograms of H2O. We just figured that out, so now we can actually put them together to solve for our molality. So we have our moles of our solute, our HCl. We have our mass in kilograms of our solvent, our H2O. And we put those two together and we get 0.360 molar for our solution.